Let's get started. So firstly, thank you to the organizers for providing the opportunity to present this work that was done jointly with Ben and Daniel, published in this paper a few months ago, in which we tried to understand the complications that would arise in detecting Sagittarius A star with BECS and some potential orbit design and mission design capabilities that we can harness to take care of them. Right, so just preaching to the choir, it seems to be that we are in the dawn of very lively baseline interferometry. From the ground, we have these incredible observations by the EHT. We have an insight into black hole astrophysics, and one of the most well-studied sources here was the black hole at the center of our galaxy, Sagittarius A star, total intensity, but we also had an image of linear polarization. And this tends to improve our understanding of how near-horizon accretion behaves and a whole lot of other astrophysical questions. From the space, we have the Black Hole Explorer mission where, compared to previous space VLBI missions, there's a promise of high angular resolution because we're now observing at much higher frequencies. Just the pertinent mission features for this talk is that we have a circular polar orbit at around 20,000 kilometers, 3.5-meter antenna diameter fixed by the fairing size, as Michael mentioned, and simultaneous dual band observations. And of course, since it's close, it's big enough, Sagittarius A star is this key science target for probing the strong lensing features. Now, just to be on the same page of the nomenclature for strong lensing, we'll talk about this photon ring, which is this strong lensing feature that is largely agnostic to astrophysical uncertainties, largely being the operative word, and how Daniel mentioned it quite succinctly in his paper with collaborators that it's a combination of images formed by photon trajectories half orbiting the black hole at least once. And so what we do is we count them using this index n, which was introduced, I think, around 5 years ago. And so what we actually see is an infinite cascade of these images. So your n equal to 0 would be the photon that comes to you directly from the accretion. Your n equal to 1 would make one half orbit, strongly probe the lensing, and then reach the observer. And so with BECS, the goal is to resolve out the n equal to 0 and n equal to 1 contributions, with resolve again being the operative word here. But what are the baseline requirements to get the photon ring? So the guiding light for this was this calculation that we did with Daniel in a paper last year, in which we noted that BECS is expected to be sensitive to the photon ring signature in linear polarization. And so based on the formula, we had that, okay, assume your geometric photon ring signal is made up of concentric Gaussian rings. You fix the Sagittarius star's total flux from observations. You assume the ring thickness from simulations because that's still poorly constrained. The photon ring signature in linear polarization will start to dominate at this radius of 13.5 gigalambda. And it's a fairly clean result, and this number will reappear again in the not so distant future. But the story is not that straightforward. There are astrophysical complications. In particular, the radio observations of the Sagittarius A star are affected by scattering from the ISM, for which several mitigation strategies exist. But at least the outlook of this paper that a lot more can be done to look at the opposite vector of research, in which we use radio observations to actually study the properties of the ISM. And so the regimes of scattering that we work with, firstly, is the snapshot regime, where we only average over the source noise. Our focus here was the so-called ensemble average regime, where you have an unscattered image, which is blurred by this deterministic diffractive kernel. And we also have the average regime, where you have these large-scale gradients in the image that lead to these tears and distortions, but we're only. So how does turbulence comes into all this? There are three parameters that we need to be interested in. First of all, is the power law index of the structure functions of this phase fluctuations that arise due to this thin scattering scheme that's present between the source and the observer. Next is the inner scale of the turbulence, which characterizes where this power law dissipates. And third is the outer scale of the turbulence, which characterizes where this turbulence cascade kicks in. So between these two regimes, you have a power law, you have an inner scale, and the outer scale for this study was kept to be fixed to be a pretty large distance. And that's how it's done in stochastic optics in the EST imaging package, if you're interested. And so this is what our donuts look like. So these are the donuts. You're using different interstellar doughs. What you notice here is three parameter sets. The first parameter set for alpha and Rn was recommended from the Johnson 2018 paper based on archival radio observations. The second parameter set of 1.67 and Rn 600 makes contact with the standard Kolmogorov theory of turbulence in the ISM. And the last one is this limit of the shallow range from ISM theory of alpha being between 0 and 2. And there is a robust inner scale limit again arriving from archival radio data. Now, when you look at these images, it's good news because all of these parameters don't seem to be too crazy because the images look pretty similar. But that also makes your life very difficult because just looking at the images, it's very difficult to discern which parameter choice is being looked at here for the source. Now, if you have to choose the parameters, you have to look at the Earth stations that you want to form with BECS. So we looked at 3 stations here to form the BECS Earth baselines. One was ALMA, which is the most sensitive, the sub-millimeter array, which is moderately sensitive, and this SMT, which is suboptimal sensitivity. And so the key question that we pose is the following. Recognizing uncertainties in the ISM parameter space, can BECS observe Sagittarius star at all? And so time for results. So this is something that we call the detectability matrix, where we are varying not just the baseline lengths, but also the parameter space. The plot is a little busy, so let's break it down. So first, we look at the global breakdown. So if you go from top to bottom, you are now varying your baselines with respect to BECS. So your BECS Earth baselines. If you're going from left to right, you're now varying the ISM parameters, and it's the same set of 3 parameters that we looked at earlier. And on the color bar, you have this visibility amplitude, which is basically the total flux in the Fourier domain. Now we have a local breakdown. So this is just a sample plot. Here, the red points are the points that are sampled by the BECS Earth baselines over 1 day of observation. The color bar represents how much accessible flux you have. The gray region is the inaccessible flux you have, and this cutoff is arising from the sensitivity calculations, and you want your flux to be 3 sigma above your thermal noise limit. And black is this circle of 13.5 giga lambda, beyond which we expect the photon ring signal to dominate. So what do we want? We want more red points on the colored regions outside the black circle. And that's the way to sort of interpret this matrix. And we can now look at the results again. So if you focus your attention to the top left corner, let's say we are at BECS ALMA, you go from left to right, you notice that as you increase your value of alpha, your amount of accessible flux goes down. Now, if you keep your attention at the same point, but go top to bottom, you will notice that for the same value of alpha and Rn, you go to your suboptimal sites and you reach the BECS SMT baselines, and there's just no overlap on the accessible signal at all. The good thing here is that at least from observations, the alpha equal to 1.38 set seems to be favored and 1.9 is disfavored, which is good for us. But then again, suboptimality of baselines is something we need to be worried about. And so based on this, the key inferences that we had for BECS ALMA, across all variations in the parameter space, the proposed baselines have access to the signal, which is great. For BECS SMA, you start to lose out on the signal on these longest baseline that BECS is making. But for BECS SMT, there was just no accessible signal available over this observing time frame. But an important discovery that we found here was that there's much more accessible signal across a parameter space on baselines that are actually shorter than the final BECS baselines that's being proposed. So our proposed mitigation strategy was to use orbit transfers, and a good deal of the paper is dedicated to using state-of-the-art or rather currently used propulsion choices to see if whether this can be done. In a conversation with Janice Houston in July 2025, I was told that, yeah, that's not happening for BECS, this phased migration scheme, but in this current proposal posture. But if BECS is successful, we just heard that it's just the beginning. And yeah, that's about it. Thank you so much for your time. And if you have any questions, please feel free to get in touch.
Thank you so much. Questions?
That's not very encouraging.
From a co-author, Daniel, go for it.
Yeah, I mean, it's been a while since I thought about this problem, and I've been out of touch with the I guess the relevant subfield for a while. So I'm curious what your impression is. I guess what are there observations you can think of that would push you towards, I guess, more optimism in the scattering model? I know Michael and folks have been sort of thinking about modifications to to the scattering model that might be going in a good direction, but is there some observation you can pinpoint that could be carried out that would retire sort of scattering risks for a Sagittarius star? And I guess that if you want to lead off the discussion, I'd also love to hear what other people are thinking about this.
I mean, if I'm being honest, from the radio observation standpoint, we seem to be doing okay because the constraints on alpha and Rn from the 2018 paper seem to, which are again radio constraints, but they seem to be indicating that this 1.38 regime seems to be a good bet, at least from radio. Now, there are ways to mitigate that if you look at these long baseline models that you have for refractive scattering, there were these various ways that you can model scattering. You have this boxcar model, you have this von Mises distribution, and this tend to affect whether your scattering is more on the major axis or the minor axis, and whole sort of complications arise. But if it's just a parameter choice, I think we are okay for the most sensitive baselines.
Great.
Okay.
Glad to hear it.
Yeah, I guess I really like that you're doing this project, and I worry that we have false certainty in the properties of Sagittarius star scattering. And to put this in context, I think until 2013, everyone kind of knew that the scattering was local to the galactic center, and the predictions on the temporal broadening were wrong by a factor of 1,000 at L band. So it is possible that we'll go to these long baselines and realize that something was just fundamentally broken with our modeling efforts, and we're making pretty sweeping conclusions based on a handful of data points about how the scattering changes. But I'm curious if you just have any intuition about is there some direction that we're just totally blind to at the moment that would dramatically change the consequences here from you tinkering with these specific parameters?
Okay, so there are two answers to this. One of that is an astro answer, and the other is a practical answer. The astro answer is it's very difficult to say that unless you've done the same analysis with refractive scattering, because diffractive seems to be pretty nicely favored. It's a convolution, it's a deterministic kernel, sure. But unless you do the same analysis with refractive scattering along baselines, you wouldn't know, and somebody has to do it. The practical consideration here is that no, you don't have 20 ALMA sites, right? You have one ALMA, and then you have everything else that is either suboptimal or not optimal at all. So then the practical question you'd want to ask is that, assuming your most pessimistic assumptions about scattering, would your Earth array still get you signals on these long baselines? Because the amount of inaccessible flux that you have to this photon ring is directly governed by the sensitivity. And for sensitivity, if you fix BECS, you need to vary the Earth sensitivity stations, and that is something you can't change. So an analysis that needs to be done here is the most pessimistic assumptions. You assume your worst parameter set, you assume refractive and diffractive scattering, and you assume your all kinds of array on the Earth. Do you still have any accessible flux beyond this photon ring regime? But unless somebody does that calculation, it's very hard to say.
I think it would be very interesting to take your extreme values and see how they look at 3 millimeters, and check with Sarah about whether that's testable.
And I mean, it's not like it's my extreme values. It's just that the ISM has this range of alpha between 0 and 2, where things should be okay. And something less than 2 is 1.99. So there you go.
The Tamar bounds. Yeah. Daniel, go for it.
I'll just add in for all of the values that Aditya used, they all reproduce the long wavelength broadened sizes correctly.
Well, the asymptotic Gaussian, but 3
That's right.
millimeters is kind of
The interesting sort of sticky wicket. Yeah, that's true. We should.
yeah. Okay.